G'day guys, welcome to this video where we're going to look at SPI support or SPI support on the BUSSide. SPI is a popular interface used in embedded devices, and you commonly see it in things like embedded flash memory for bootloaders, firmware on embedded devices and so forth. You might also see it in sensors and other things that require sort of a low speed communications bus within an embedded device. So on the right I've got a picture of a SPI flash memory chip in the adapter that's been provided with the BUSSide, and this is conveniently, you can put a SOI8 or a SOP8 IC into the adapter and plug it directly in the BUSSide and then access that flash memory. So let's start the BUSSide. Just plug it in again, and there we go. We have our help screen that comes up, and we can see we've got a lot of commands associated with SPI. Now, we can also connect our BUSSide without using this adapter, which plugs in a flash chip, but we can try to plug in the GPIOs directly to points on an embedded device, a device under test, and try to determine if these particular pins or test pads or test points are SPI themselves. And if we just connect all of those points to our GPIOs on our BUSSide, we can run a command like SPI discover pinout, which will attempt to brute force all possible combinations of those GPIOs and SPI wires to see if there's a SPI interface associated with this particular chip. And there we go, we found a SPI chip. There was some communication issues with our BUSSide while we were doing that. We saw those retransmits, which indicates that our cable may have had some issues. But we can run that again, and we'll see how fast it comes up. And there we go, we got it again without any retransmit. The BUSSide is actually quite resilient against communication errors. It uses a process of checksums and retransmits and synchronization words and sequence numbers and so forth. Try to ensure that it correctly communicates between the device and your host computer. So in this particular case here, we saw that it has correctly identified a SPI interface, which is in particular this SPI flash memory, and it's identified the 4 wires associated with SPI. SPI is a 4-wire protocol, has a chip select, which is useful in when you have multiple slaves. It has a clock and it basically an input and output. It is full duplex, so it can both transmit and receive at the same time. So we've identified a SPI interface, in this particular case our SPI flash memory. What we can do next is interrogate the chip and send a command directly to it and ask for its flash ID. If it is flash memory, it should respond with a particular ID unique to that manufacturer and chip. So let's send a command on the default GPIOs associated with this adapter that we're plugging into, and let's send the read ID, which is a 1-byte command 9F, and then it will read 3 bytes as a response. So let's send that, and we get a response immediately. It is full duplex, so as we send out a command on the bus, we can read at the same time. So this first response is that associated with that 9F, but the EF40 and 17 are associated with our chip ID, which we use to determine things such as how big the flash memory is and so forth. So we can send this command natively using the SPI flash read ID command, and we get the same response. And this is actually how flash ROM users can determine the amount of flash to read and so forth, and the type of chip that it is based on this particular ID. Another thing we can do is read another type of ID, a unique identifier associated with the chip. And this chip, every individual chip is supposed to have a unique ID, and it's not programmable once it's been programmed at one time at startup, at manufacturer time or vendor time. And the idea is this is possible to implement some sort of copy protection and so forth, or identification of particular devices based on their unique ID. It is one-time programmable, but in reality you can just buy from the manufacturer a bunch of unprogrammed chips and then write whatever ID that you want. Effectively, it's a sort of akin to those magic cards for RFID where you can write to the device. So there's our unique ID. Now we know that it's flash memory. It responded to our flash read ID command. Let's dump 4096 bytes 4K to 1.bin. Oops, SPI flash dump 4096 1.bin. I'm not having a great time here. 4096 1.bin. And now we've dumped that flash memory. So let's look at what we got. Okay, and we can see and recognize sort of fairly quickly that this is a bootloader for Linux, and these are things like the bootloader or kernel arguments. If we wanted to, we could modify these kernel arguments so that we could boot into single user mode and gain access to the device. We can write to the chip as well as read it. So that's what we get when we look at that particular flash ID. Another thing we can do is use flash ROM directly, and I'll show you how to do that shortly. Now, there's one interesting thing about SPI is that it's and these types of chips is that they're command orientated, and that they respond to commands that you send them. Typically one or two byte commands. So what we can do with the BUSSide is try to enumerate the possible set of commands that this SPI chip implements. So we'll use our GPIOs associated with our adapter pins, and we'll try to enumerate these commands, and it successfully found 6 SPI commands. Now this chip actually implements more than 6 SPI commands, but due to the limitations in how it detects a response, it requires sort of output to be sent from the slave device back into the master. But it has identified 6 commands, and we can see that chip ID command that we sent to 9F and then received a few 3 bytes in response. It has identified that particular command as well. Now we can look up the data sheet with every one of these commands and verify that they're implemented, or they're documented rather, and this gives us the potential to discover undocumented SPI commands. Now this particular chip, all of these commands are documented, so we don't have hidden functionality in this particular chip, but you probably just need to look at a wider array of chips and you'll probably find something there. So let's exit out of our client, and we'll look at the flash ROM implementation that we have with the BUSSide. Flash ROM is a piece of software that's used for accessing flash memory using things like SPI. And we've got a BUSSide driver that's been implemented. It's on the GitHub. And we're just going to interrogate the chip and see if it identifies it. And it has actually identified a WinBond flash chip that's 8 meg in size. The next thing we want to do at this point is dump that flash chip. And we can use this particular command in flash ROM to dump the chip or read the chip. If we run this, it would probably take about 3 or 4 minutes to dump the flash chip. We won't wait that long. We'll just go back into our, and I'll show you one I've prepared earlier. So this is our chip that we've dumped already, and it matches up with what we saw earlier when we just dumped 4K. These retries down below are totally acceptable, by the way. It just means that there was a checksum failure in communicating between the bus side and your host computer, and it's quite normal to get retransmits as part of a normal operation. So let's go back into our image. Once we've got the image, what we want to do next is run binwalk on it. And binwalk will look into the image and try to identify embedded content. And in this particular case, we can see we've got a squash file system, which makes sense because this is a Linux embedded device that this chip was taken out of. So let's extract. Let's extract the image, have a look around. And now we can see an embedded Linux file system on this particular device. And we can see that it's a MIPS system, which makes sense for our embedded devices. So thank you very much, guys. That's pretty much all I've got to show you in this video. But definitely watch the other videos for more information about the BUSSide. And if you like this type of content, we offer training at InfoSect on interfacing with IoT devices and a bunch of others where we'll do stuff like this and use the BUSSide as well. So thank you very much. I hope you enjoyed the video, and I'll see you guys next time.